Welcome back, ladies and gentlemen. Today we are going to finally get to our last point of concurrency in our Chapter 6, point of concurrency focus. We've gone over the circumcenter. Remember, that is created by the perpendicular bisectors. We have gone over the incenter, that is created by the angle bisectors. We just went over the centroid, that is created by the medians. And last, but certainly not least, we are taking into account the orthocenter. And the orthocenter is created by what we know as the altitudes. Now think about it. What do you think of when you think of the word altitude? Hopefully you think of the word height, right? A lot of people think of height. You can, in a sense, somewhat kind of think about it as the height from each of the vertices of a triangle. Specifically, the altitude of a triangle is the perpendicular segment from the vertex to the opposite side or to a line that contains the opposite side. This is important because of what would happen if it's an obtuse triangle. Okay, so the perpendicular line or the segment to its opposite side may not actually hit the opposite side. It could hit a line that contains the opposite side. So what is so special about the orthocenter? What's so special about the orthocenter is that there's nothing special about the orthocenter. Really, there's no characteristic. Notice that there's not a orthocenter theorem that goes along with it. So it does not have an interesting characteristic like the other three did. The only thing we will be focusing on with the orthocenter is its placement, and specifically its placement on a order or a coordinate plane. So where can we expect it? Well, pretty similarly to how we had for our circumcenter, it can be found inside of an acute triangle, on a right triangle, and outside of a obtuse triangle. So let's talk here for a sec. This is crucial with the right triangle because it's a specific placement. The orthocenter can specifically be found at the vertex in which the right angle is found of the triangle. Why? Well, if you think about it, the perpendicular line from vertex straight down is the side of the triangle. Same thing on over here. The perpendicular segment from vertex to the opposite side is the actual side of the triangle. So we would have our vertex here at point P also being our orthocenter. And then last but not least, for the obtuse, here's what we were talking about in our last slide. As you can see, from this vertex to its opposite side, you notice that not every single one is necessarily hitting a side of the triangle. Some of them are hitting a line that contains the side of the triangle. And so that's why it ends up kind of being outside of the triangle, as it may not actually hit the opposite side. It's that line that contains it. So let's take a look at one example of how we can find it on an ordered pair. So it says find the coordinates of the orthocenter. So unfortunately, we don't have a formula like we do for our centroid, but we can utilize what we know about its placement to find the orthocenter. So let's take a look. Let's go ahead and find out where our points lie. At -5, -1. At -2 and +4. 1, 2, 3, and 4. And Z is at 3, -1 right there. All right, so there is where our orthocenter, or excuse me, our triangle will be found. Let's go ahead and try to connect all these and make ourselves a nice triangle. And there we are. All right, so we've put ourselves in a position now where how do we physically find said orthocenter? Well, the key to identify is where is it going to be? Is it acute? Is it a right? Or is it an obtuse triangle? And we can use that to figure out where it's actually going to be. Well, it looks like it may possibly be a right triangle in here, right? But this one actually does not come out to be a right triangle. It's going to end up being a acute triangle, and so we can expect it somewhere on the inside. And we can always check that by finding the slopes of these two lines and seeing if they were opposite reciprocals. They were not. So what I want to do first and foremost is I want to always take into account the easiest altitude to find. Well, remember, it's from vertex perpendicular to its opposite side. This is fantastic when it's a horizontal line because its opposite side is horizontal. The orthocenter will easily be a vertical line, and so boom, there is my orthocenter right through the point x equals -2. And so let's go ahead and identify this line. This line is the line x equals -2, the line in which every x value is -2. That is that R2 that we have right there. The second thing I want to think about is, well, where will another one be? Well, these two lines clearly are not horizontal or vertical, so that makes it a little bit of a challenge for us. We want to actually go ahead and find the equation of the line including this point and is perpendicular to the opposite side. Let me say that again. We want to find the line that is including this point and is perpendicular to its opposite side. So let's find out what the slope of this line is first, and that way we can go ahead and find out what the opposite reciprocal slope could be. So this is the point, this is y, and z. We're going to find out what the slope of yz is. So the change in y is -1 minus 4 over the change in x. So we have -5 over 5, which equals -1. So that means the perpendicular slope will end up being a +1. So using slope-intercept, or point slope or slope-intercept, but I'm actually going to use point slope. I made a mistake. I'm going to use point slope. So we're going to do y minus y1 equals m times x minus x. Again, that's point slope form. And so then you're maybe asking, well, how do I actually find out all these particular points? Well, let's find out where this line is. This line has to include this point and be perpendicular, maybe somewhere through there, right? So the point that I know is the point x. So there's my y1 and my x1. So I have y minus y1, which is a positive, equals slope of 1 times x minus x1, which is really a +5. So the equation for this line ends up being y equals x plus 4. So let's just see where we are right now, okay? This right here is the equation of the blue line that I just drew. We have also the line x equals -2. So we need to find out the exact point of intersection. Well, how do I do that? Well, I know for sure that every x value on this first altitude is -2. So if I can take this x equals -2 and substitute it into there, I will find out what the other y value is at this point. So y equals -2 plus 4, and -2 plus 4 is 2. So I can find my orthocenter at -2, +2. Okay? Now again, if you need to rewatch the video, that's the glory of it being on video. Rewatch it, maybe go through those steps one more time.